takes billions of years for uranium to form deep within the Earth. Yet a piece no larger than your fingertip can produce as much energy as more than 3 tons of oil. This seemingly ordinary material sits at the center of 2 opposing worlds. On one side, a power source that fuels modern civilization. On the other, a force capable of disrupting global stability. But have you ever wondered how humans extract and process tens of thousands of tons of uranium every year, one of the most dangerous materials on Earth, and turn it into a stable, controllable source of energy? Today, join Agriculture Insight as we uncover that entire process, where a raw mineral is transformed into a force powerful enough to run the modern world. Uranium is one of the oldest elements on Earth, formed in stellar explosions billions of years before the planet itself came into existence. Yet it wasn't until 1896 that humans truly took notice, when Henri Becquerel discovered that uranium could emit invisible rays without any external source of energy. This discovery marked the beginning of nuclear physics. From tons of raw uranium ore, Marie and Pierre Curie went on to isolate 2 even more radioactive elements, radium and polonium, laying the foundation for our modern understanding of nuclear energy. What makes uranium remarkable is not its appearance, it looks like ordinary rock, but the immense energy it holds. In nature, about 99.3% is uranium-238, while only 0.7% is uranium-235. Yet it is this tiny fraction that can undergo fission, triggering a chain reaction and releasing enough energy to power an entire city. Because of this property, uranium is used in nuclear power plants to generate electricity for millions of people, while also serving as the core material in nuclear weapons, one of the most influential technologies in human history. From Hiroshima and Nagasaki to the nuclear arms race of the Cold War, uranium has played a critical role in shaping the global balance of power. Now, let's descend deep beneath the Earth, through dark tunnels and into a harsh, unforgiving environment, to northern Saskatchewan, Canada, one of the world's largest uranium capitals, where the journey of one of the most powerful energy sources on the planet truly begins. Uranium mining takes place far below the surface, at depths of around 450 to 500 meters, where ancient rock layers encase energy-rich ore bodies. Before reaching the ore, engineers must overcome a major challenge: high-pressure groundwater. If left uncontrolled, it can flood the site at any moment, causing tunnel collapses or halting operations entirely. To address this, they rely on an unusual method: ground freezing. Hundreds of steel pipes, often up to 200 in total, are drilled around the ore zone. A chilled solution is circulated through them at around -30°C, freezing both the soil and groundwater into a solid shell that stabilizes the area and prevents water intrusion. Once conditions are fully controlled, drilling begins with near-perfect precision. The drill heads are fitted with tungsten carbide buttons, nearly as hard as diamond, capable of penetrating rock formed over billions of years. The process starts with a small exploratory hole, known as a pilot hole, to pinpoint the exact location. From there, larger drills expand the access path, breaking the ore and allowing it to fall into collection chambers below. Most of the system is operated remotely, minimizing human exposure in a high-pressure radioactive environment. Even so, the challenge remains. Just a slight deviation during drilling can impact the entire operation. A single borehole can take hours, even days to complete. Once separated from the rock, the uranium ore is transported using mine carts running on rail tracks deep underground. Each train typically consists of 10 to 20 connected carts, moving slowly through narrow tunnels only a few meters wide, where light is almost non-existent. Each cart can carry several tons of ore, and the system operates nearly continuously, creating a steady flow of material from the extraction zone to collection points. Once brought to the surface, uranium ore is, in essence, just ordinary rock. The uranium itself remains locked inside, bound tightly within the mineral structure, and without breaking that structure apart, there is simply no practical way to extract it. To make that possible, the ore is gradually reduced in size through a series of crushing and grinding stages. Large chunks are first fed into industrial crushers, where they are broken down into smaller pieces, typically around 5 to 10 centimeters. From there, the material continues through additional grinding processes, each step reducing it further, down to just a few millimeters. Even then, the material is still too coarse. Inside ball mills, large rotating drums filled with heavy steel balls, the ore is continuously tumbled and ground for hours. With each impact, the particles become finer until they reach a size of about 0.1 to 0.3 millimeters, almost like fine sand. This level of refinement is necessary because uranium does not exist in isolation. It is embedded within the surrounding rock. By reducing the material to such a fine scale, the surface area increases significantly, allowing the chemical processes that follow to access and separate the uranium much more efficiently. The final step in this stage involves mixing the powdered ore with water to form a slurry, typically containing around 40 to 50% solids. In this form, the material can be pumped, moved, and processed with precision, marking the transition from raw rock to a controlled, workable feed for the next phase of extraction. Once ground and mixed into a slurry, the uranium ore enters the extraction stage. The mixture is transferred into large tanks, where sulfuric acid is added to dissolve the uranium. This process takes place under controlled conditions and typically lasts several hours, with continuous agitation to ensure even contact. Rather than breaking down all the material, the acid selectively targets the uranium, allowing it to dissolve into the liquid, while most of the surrounding rock and minerals remain in solid form. Once the reaction is complete, the mixture separates into two distinct parts: solid residue and a uranium-rich solution, which can contain up to 80 to 90% of the original uranium content. This solution is then collected, becoming the primary feed for the next stages of refining. Once uranium is in solution, the next step is to recover it in solid form. Heat and chemicals are carefully controlled to remove excess water, allowing uranium to crystallize into tiny particles that settle at the bottom over several hours. The resulting material is then dried into a yellow-brown powder known as yellowcake. Its color comes from uranium oxide, making it stable and easier to transport. A single 200-liter steel drum can contain enough uranium to be further processed into fuel. Although it looks quite ordinary, yellowcake is a globally traded material used by uranium enrichment facilities. And unlike what movies suggest, it does not glow. Just a simple yellow powder that holds an immense amount of energy. After being concentrated into yellowcake, uranium is still not ready for use. In its solid form, it isn't suitable for the next critical step, enrichment. To make that possible, it must be transformed into an entirely different state, a gas. To do this, yellowcake undergoes a series of chemical reactions, converting it into a compound known as uranium hexafluoride, UFC. What makes this substance unique is that it can turn into a gas at a relatively low temperature, around 56 degrees. This property allows uranium to be fed into enrichment systems, where even the smallest differences between isotopes can be precisely separated. At this stage, the process is no longer about handling material. It becomes a matter of fine-tuning at the atomic level. In nature, uranium is almost unusable. Only about 0.7% of it is U-235, the isotope capable of sustaining a nuclear reaction. That fraction is so small that, without intervention, the entire mass of uranium holds very little practical energy value. That's why facilities rely on specialized machines known as centrifuges. Inside them, uranium gas is spun at speeds of up to 50,000 revolutions per minute, fast enough to create forces capable of separating incredibly small differences in mass. The heavier uranium is pushed outward, while the lighter portion, U-235 moves closer to the center. This process is repeated across hundreds of stages, each making only a tiny adjustment, but together producing a significant effect. After many such cycles, the concentration of U-235 is increased to around 3 to 5 cent, just enough for the uranium to truly come alive and be used as fuel in nuclear reactors. After enrichment, uranium is no longer kept in its gaseous form. The UF gas is cooled and converted back into a solid, then undergoes further chemical reactions to become uranium dioxide, UO2, a more stable form suitable for fuel fabrication. At this stage, uranium begins to take shape again as a fine black powder. From a nearly invisible gas, it is transformed into a material that can be handled, processed, and precisely controlled. These powder particles are then tested for purity and size to ensure uniformity before moving on to the next stage. From this seemingly simple powder, uranium will be pressed and shaped into fuel, a small change in form, but a major step in its practical use. From a fine powder, uranium dioxide is pressed under high pressure into small pellets, each only a few millimeters in size, resembling simple tablets. Despite their size, each pellet contains a remarkable amount of energy. These pellets are then placed into furnaces and heated to around 1600 degrees Celsius. This process, known as sintering, removes internal pores and increases density. Under such extreme heat, the uranium dioxide particles bond tightly together, forming a solid structure. The result is a fuel pellet with ceramic-like hardness, highly durable, heat-resistant, and stable enough to operate inside a nuclear reactor for years. From a fine powder, uranium has now been shaped into a compact and reliable form, ready for the next stage of assembly and use. Once formed into fuel pellets, they cannot be used immediately, and must be assembled into a complete structure. Each pellet is stacked in sequence inside zirconium tubes, a special metal that can withstand high temperatures and does not interfere with the nuclear reaction. Once the tubes are filled, both ends are sealed, forming fuel rods. Each rod contains dozens of pellets aligned in a straight line, designed to operate reliably under extreme temperature and pressure conditions. After the fuel rods are completed, they are not used individually but are assembled into fuel bundles. Each bundle typically consists of around 30 to 40 rods, most commonly 37, arranged in parallel and secured by a metal frame to maintain precise spacing between each rod. But the journey doesn't end here. Have you ever wondered how electricity and other forms of energy are generated from these uranium fuel bundles? Once the fuel bundles are fully assembled, they are placed into the reactor core, where the entire energy transformation process takes place. Here, uranium atoms begin to undergo fission. When an atom splits, it releases heat and neutrons, which in turn trigger further reactions. This creates a continuous chain reaction, generating an immense amount of heat. Inside a reactor, temperatures can reach around 300 degrees Celsius, enough to boil water and produce high-pressure steam. This steam drives turbines spinning at thousands of revolutions per minute, powering generators and producing a steady flow of electricity. A single reactor can supply power to hundreds of thousands to millions of homes, all originating from reactions occurring at the atomic level. After a period of operation, the fuel inside the reactor gradually becomes less effective and is removed. Although it no longer generates energy, it remains extremely hot and radioactive, so it is placed in deep cooling pools, where the water both absorbs heat and acts as a protective shield. These fuel bundles can remain in the pool for years, even decades, before being transferred to long-term storage systems. At this point, many people wonder, what would happen if someone fell into one of these pools? And could the water be safe to drink? The answer is that the water in these pools is actually highly filtered and strictly controlled, making it technically very clean. But don't rush to drink it. The real danger isn't the water, but the fuel rods below. If you get too close, the radiation can damage cells, cause radiation burns, and affect internal organs. So while the water may look clear and harmless, this remains one of the most tightly controlled environments in the entire nuclear industry. Today, the United States is the largest oil producer in the world, with production reaching nearly 13 million barrels per day. Among all states, Texas plays the central role, producing over 40% of the nation's total oil output. Some even say that if Texas were an independent country, it would rank among the world's top oil-producing nations. However, the United States is also the largest consumer of oil on the planet, despite having only about 4% of the world's population, a relatively small share compared to its enormous energy consumption. As a result, fuel prices in the US are a highly sensitive economic issue. When fuel prices rise, transportation and goods become more expensive, which directly affects inflation and can even influence elections. To protect its energy security, the United States established the Strategic Petroleum Reserve, the largest emergency oil reserve in the world. It can store more than 700 million barrels of oil in massive underground salt caverns. This system was created after the 1973 oil crisis, ensuring that if global oil supplies are disrupted, the US economy would still have enough energy to keep running. For this reason, oil is not just a fuel, it is also a strategic resource closely tied to the economic and political power of the United States. Now let's travel back hundreds of millions of years to see how the black gold that powers our world today was truly formed. Around 100 to 300 million years ago, ancient oceans were filled with countless algae and microscopic marine organisms. When these organisms died, their remains sank to the seafloor and were gradually buried beneath layers of mud and sediment. Over time, the immense heat and pressure deep within the earth transformed this organic material into hydrocarbons, the fundamental components of crude oil. These hydrocarbons then migrated through porous rock layers and became trapped in geological formations known as oil traps, deep beneath the ground or ocean floor. After accumulating for hundreds of millions of years, they formed vast oil reservoirs that today require drilling as deep as 10 to 12 kilometers into the earth to reach. But how do humans manage to find oil reservoirs buried kilometers beneath the Earth's surface? The answer begins with the stage known as oil exploration. Long before any drilling rig appears, geologists must first see deep underground using seismic surveys. Specialized vessels send powerful sound waves down into the ground or the ocean floor. When these waves encounter different rock layers, they bounce back and are recorded by thousands of sensors. Using this data, computers construct detailed 3D maps of geological structures located 2 to 5 kilometers beneath the surface. Even so, searching for oil remains a high-risk endeavor. On average, only about 1 out of 10 exploration sites ultimately contains oil in quantities large enough to be commercially viable. But if a promising oil trap is discovered, the reward can be enormous. Such a reservoir may hold hundreds of millions of tons of crude oil, a massive energy resource capable of powering entire economies for decades. Most offshore drilling rigs are constructed in large shipyards and industrial ports, where massive steel frameworks are welded together into modules. A single rig can weigh 10,000 to 30,000 tons, equipped with a towering drill derrick, heavy cranes, power generators, living quarters, and even a helicopter landing pad, essentially a small industrial city at sea. Once completed, the entire structure is transported by heavy lift barges or specialized vessels to the oil field, often located 100 to 300 kilometers offshore. At the site, engineers lower the steel jacket structure to the seabed. Giant steel piles, sometimes over 100 meters long, are driven deep into the seabed sediments and secured with concrete to create a stable foundation. After that, the deck of the drilling platform, weighing thousands of tons, is carefully lifted and placed onto the jacket using super heavy cranes with remarkable precision. Only when this steel city is fully installed amid the waves of the open ocean can drilling operations finally begin, opening the path to oil reservoirs hidden kilometers beneath the Earth's surface. Once the drilling platform is firmly anchored in the ocean, the real work begins: drilling the oil well. From the top of the derrick, which can rise dozens of meters high, steel pipes about 9 to 10 meters long are connected one by one to form a massive drill string that slowly penetrates deep into the earth. At the tip is an ultra-hard alloy drill bit that rotates continuously, crushing ancient rock layers located 2 to 5 kilometers beneath the surface. Throughout the process, a special fluid known as drilling mud is pumped constantly down the well. It acts like the lifeblood of the drilling system, cooling the drill bit, stabilizing the well walls, and carrying rock cuttings from deep underground back to the surface for engineers to analyze. Drilling a single well can take several weeks to several months, and offshore projects can cost 50 to 100 million USD per well. Today, many wells are not drilled only vertically, but also horizontally, for an additional 1 to 3 kilometers, allowing access to more oil-bearing layers within the same reservoir. But at these depths, geological pressure can exceed 10,000 psi, hundreds of times greater than atmospheric pressure. For that reason, every meter of drilling must be carefully controlled, because even a small mistake can trigger a dangerous oil blowout. When the drill bit finally penetrates the oil-bearing rock layer, the well enters its most critical stage: oil production. Inside the well, engineers install production tubing to channel the fluid from several kilometers underground up to the surface. In many newly discovered reservoirs, the natural pressure within the oil-bearing formation can be strong enough to push the oil upward on its own, like a massive underground spring suddenly released. However, this natural flow usually lasts only during the early stage of production. As reservoir pressure gradually declines, mechanical pumps or electric submersible pumps (ESP) are installed to maintain the flow. A modern industrial pump can lift 15,000 to 20,000 barrels of oil per day, operating continuously several kilometers beneath the Earth's surface. It's important to note that the fluid rising from the well is not pure oil. Instead, it is a mixture of crude oil, natural gas, water, and fine sand carried up from the surrounding rock layers. For this reason, at the drilling platform or nearby gathering station, the mixture is directed into high-pressure separators, where oil, gas, and water are separated into different streams. This is the first stage of processing, before the crude oil is sent through pipelines and continues its journey to oil refineries. When the fluid from an oil well reaches the surface, it is not pure oil but a mixture of crude oil, natural gas, water, and fine sand. In many oil fields, the actual oil may make up only 60 to 70% of the mixture, while the rest consists of water and gas. For this reason, the mixture must first be sent into high-pressure separators installed directly on the drilling platform. Inside these separators, the pressure is reduced so that the components can separate naturally based on density. Natural gas, being the lightest, rises to the top and is collected to be compressed into gas pipelines or re-injected into the reservoir to maintain pressure. Crude oil forms the middle layer and is directed into temporary storage tanks. Meanwhile, water and sand, which are heavier, settle at the bottom and are removed for separate treatment. After this initial separation, the crude oil becomes stable enough for transportation. It is then pumped into subsea pipelines stretching hundreds of kilometers or transferred to oil tankers capable of carrying millions of barrels, beginning its journey to refineries on land where it will be transformed into gasoline, diesel, and many other petroleum products. Not all oil reserves lie beneath the ocean. On land, oil extraction takes place in a more familiar setting but remains just as complex. Once a well reaches the oil-bearing layer, crude oil is brought to the surface through production tubing. In the early stage, natural pressure in the reservoir may push the oil upward on its own. But as the pressure declines, mechanical pumping systems begin to take over, the most recognizable being the pump jack, the machine with a rhythmic metal arm often seen in onshore oil fields. Each pump jack works like a giant underground syringe, drawing oil from depths of about 1 to 3 kilometers below the surface. A typical onshore well can produce 20 to 300 barrels of oil per day, depending on the size and richness of the reservoir. In major oil regions, such as the Permian Basin in Texas, where more than 7,000 wells are currently operating, thousands of pump jacks move up and down day and night, forming vast fields of pumps stretching across the landscape. The fluid brought to the surface is still a mixture of oil, gas, and water, so it must first be separated at nearby gathering stations before the crude oil is sent through pipelines or tanker trucks to refineries. From these slowly moving machines scattered across dry fields, a resource formed over hundreds of millions of years begins its journey into the modern global economy. After leaving the oil fields, crude oil is transported to oil refineries, facilities where one of the most complex industrial processes in the world takes place. A large refinery can process 300,000 to 600,000 barrels of crude oil per day, operating continuously around the clock. The most important step in this process is fractional distillation. First, crude oil is heated to about 350 to 370 Celsius, turning it into vapor before it enters a distillation tower that can rise dozens of meters high. As the vapor moves upward inside the tower, different hydrocarbon compounds condense at different heights depending on their boiling points. The heaviest fractions, such as asphalt and lubricating oils, condense near the bottom. Above them are diesel, followed by kerosene and jet fuel, while gasoline condenses closer to the upper levels. At the very top of the tower are light gases such as propane and butane. However, the products obtained at this stage are still not fully ready for use. Many hydrocarbon molecules remain too large or do not yet meet fuel standards. They must undergo further processes such as cracking, which breaks large molecules into smaller ones, reforming, which improves fuel quality, and blending, where different components are mixed to meet precise technical specifications. Through this chain of processes, a single 159-liter barrel of crude oil can be transformed into gasoline, diesel, jet fuel, and thousands of petrochemical products that power the modern global economy. During the extraction of petroleum, crude oil is often produced together with large amounts of natural gas. When oil companies do not yet have the infrastructure to capture or transport this gas, they carry out a process known as gas flaring, which involves burning the excess gas on tall flare stacks at the oil field. This practice helps reduce pressure in the well and ensures safety by preventing the buildup of highly flammable gases. However, gas flaring is controversial because it releases carbon dioxide and other greenhouse gases into the atmosphere, while also wasting a valuable energy resource that could otherwise be used to generate electricity or fuel. As a result, in recent years, many countries and oil companies have been working to reduce gas flaring by capturing and utilizing the gas instead of burning it. Although soap can be produced from many different fats such as animal fat, coconut oil, olive oil, or palm oil, sunflower oil is increasingly favored for its sustainability and environmental friendliness. Sunflowers thrive in warm climates, require about 2,000 hours of sunlight per year, and use very little agricultural chemicals, thereby minimizing negative environmental impact. The harvest season begins when the sunflower heads droop, the back of the flower turns brown, and the seeds inside reach natural dryness. Farmers use handheld moisture meters to check each batch of seeds, harvesting only when moisture content falls below 20% to prevent shell cracking and reduce oil loss. Harvesters are equipped with narrow cutting heads adjusted to the height of the flowers to cut only the heads without damaging the stalks. Inside the machine, a rotating drum gently separates the seeds from the flower head, while a fan blows away petals and large debris. Parameters such as drum speed and airflow pressure are continuously monitored to minimize shell breakage, a key factor in preserving oil quality. After separation, the seeds are collected into well-ventilated containers to prevent moisture condensation and maintain natural dryness. At the end of the day, each batch is quickly tested for moisture and impurities before being transported to the nearest receiving station, officially entering the post-harvest processing stage. Immediately after leaving the fields, trucks loaded with sunflower seeds arrive at the receiving station to begin the post-harvest processing stage. This is an extremely important step to stabilize the quality of the raw materials before oil extraction, as freshly harvested seeds still contain impurities and high moisture levels, which can lead to spoilage if not handled promptly. In the intake area, the seeds are poured into receiving hoppers and then passed through a multi-layer vibrating sieve system. Each sieve layer has different mesh sizes to remove straw, dust, shell fragments, and empty seeds. At the same time, high-capacity fans blow air in the opposite direction of the falling seed flow, carrying away lighter impurities. Only seed batches that meet the required size and weight standards are transferred to the drying stage. The drying process is carried out using continuously circulating hot air, maintained at 100 to 110 degrees Fahrenheit for several hours to reduce the seed moisture content to approximately 8 to 10%. The temperature must be strictly controlled. If too high, the fatty acid structure may be damaged. If too low, the seeds remain moist and create conditions for mold growth. Temperature and humidity sensors are installed throughout the drying chamber, continuously transmitting data to the central control panel for engineers to monitor in real time. Once the standard dryness level is achieved, the seeds are naturally cooled, then pass through a metal separator and a final sorting system to completely remove any remaining impurities. Finally, the clean, dry, and uniform sunflower seeds are stored in sealed steel silos, ready for the oil extraction stage. The moment they are transformed into a stream of golden oil, the precursor to future bars of soap. The refined sunflower oil is then pumped into the reaction vessel, the heart of the entire production line, where the most critical stage takes place, the saponification reaction. This is the chemical reaction between vegetable oil and a strong alkali, typically sodium hydroxide NaOH, producing two main products: soap, the sodium salts of fatty acids, and glycerin, a natural humectant that helps keep the soap bar soft and gentle on the skin. Thanks to its high content of oleic acid and linoleic acid, sunflower oil allows the reaction to proceed steadily, resulting in fine lather and a light texture. The oil is heated to approximately 140 to 160 degrees Fahrenheit before the NaOH solution is introduced under carefully controlled pressure. A twin helix agitator system operates continuously to ensure thorough mixing of the oil and alkali molecules. Sensors continuously monitor pH, temperature, and electrical conductivity to prevent excess alkali, a factor that could cause skin irritation. As the reaction nears completion, the mixture begins to thicken and changes color from pale yellow to creamy white or light brown, depending on the type of oil used. In the final mixing stage, natural pigments such as clay, activated charcoal, or turmeric powder are added to color the product while the soap mass remains warm. The crude soap is then separated from the glycerin solution and washed with brine to remove impurities before being transferred to the neutralization area. Although this process originates from techniques developed thousands of years ago, precise control of temperature, timing, and reaction ratios remains decisive in producing high-quality sunflower oil soap, smooth, mild, and safe for the skin. After neutralization, the crude soap is cooled and then ground into small pellets, known as soap noodles. These pellets are fed into a twin-screw mixer, where two counter-rotating shafts continuously knead the material to create a pliable, uniform texture. During this process, glycerin is added to maintain natural moisture, purified salt increases hardness, and natural essential oils such as lavender, bergamot, orange, or peppermint are sprayed directly into the mixing chamber to create distinctive fragrances. If color is desired, natural mineral pigments such as red clay or activated charcoal are incorporated at the final stage. All parameters, including temperature, viscosity, and mixing time, are strictly controlled to ensure that fragrance and color are evenly distributed throughout the entire soap mass. The result is a smooth, soft soap base with stable structure, ready for the subsequent shaping stages. After the blending process is complete, the smooth and pliable soap mass is transferred to a vacuum plotter, a machine responsible for compressing, deaerating, and homogenizing the material before shaping. Inside the extrusion chamber, a rotating screw continuously pushes the soap forward under high pressure. In the middle section of the machine, a vacuum chamber operates to completely remove microscopic air bubbles and trapped air pockets within the mixture, ensuring that the extruded soap becomes dense, solid, and perfectly smooth on the surface. Once stable pressure is achieved, the soap is forced through a steel die fitted with dozens of small concentric round openings. Under strong compression, the material is extruded into soft, uniformly colored strands, an indication that plasticity and moisture content have reached ideal levels. These strands are continuously collected on a conveyor belt, gently cooled and prepared for milling or a second extrusion to further increase density and uniformity. The vacuum extrusion stage not only provides the soap's initial form, but also determines the product's physical integrity. If pressure or vacuum levels are not precisely controlled, the finished bars may develop voids, cracks, or breakage during drying. For this reason, all pressure sensors and screw speed control systems are regularly calibrated to ensure absolute stability before the soap proceeds to the next stage. After the vacuum extrusion stage, the dense and uniform soap mass is continuously pushed through the die head, forming long bars with either circular or rectangular cross-sections. To ensure that each bar meets the exact standard dimensions required for stamping, they are conveyed to an automatic cutting machine. Here, rotating blades slice the soap bars to a pre-programmed length. An optical sensor system continuously monitors the position and movement speed of the soap bars, synchronizing the cutting blades with the extrusion rate. This precision is crucial. Even a slight deviation or a cut that is not perfectly perpendicular can prevent the bar from fitting properly into the stamping mold, leading to defects in later stages. Each cut piece is randomly inspected for weight, squareness, and surface flatness. Products that fail to meet the standards are collected and returned to the mixing stage for reprocessing, ensuring optimal material utilization and consistent quality throughout the entire production line. When the soap bars emerge from the vacuum plotter, they form continuous strips that must be divided into smaller sections before being placed into molds. This step is carried out using either automatic or semi-manual cutting systems, depending on the production scale. In industrial lines, high-speed rotating blades are fully synchronized with the extrusion rate, ensuring that each soap segment has precise length and weight. In smaller workshops, operators may use mechanical cutters controlled by a foot pedal, a solution that still ensures accuracy while allowing better control over the cut surface. Immediately after cutting, the soap billets are pushed into metal molds by a pneumatic piston inside a hydraulic stamping machine. The powerful compression force from the hydraulic system tightly compacts the soap mass, eliminating internal voids and shaping the surface according to the mold design. This is a crucial transformation step, turning freshly cut segments into solid, uniform blanks, ready for the final shaping stage and brand logo stamping. When the freshly stamped soap bars are still soft, they move to the logo engraving stage, the step that creates a distinct brand identity for each product. To Depending on the scale of production, this process may be carried out automatically using a logo stamping machine or manually with handheld molds. In large industrial production lines, steel dies engraved in relief or intaglio are lightly heated and then pressed onto the soap surface using a pneumatic piston, producing sharp and consistent imprints. In smaller artisanal workshops, craftsmen use handheld brass or steel stamps, pressing them directly onto the soap bars with controlled force. This method creates subtly unique products. Each bar may vary slightly, yet all carry a refined individuality and characteristic handcrafted value. After logo engraving, the soap bars undergo careful inspection through an optical camera system combined with manual evaluation. Technicians assess the depth and sharpness of the logo, while also checking surface smoothness, color consistency, and gloss, to ensure that every product meets aesthetic and quality standards before moving on to the final finishing stages. Products that meet quality standards are transferred to the final sorting and packaging line, ready to enter the market. After passing inspection, the finished soap bars move into the automated packaging system. Before wrapping, they are gently cooled with a stream of dry air to stabilize their structure and preserve their fragrance. Next, each bar passes through a wrapping machine using film or waxed paper, where the packaging is heat-sealed at a controlled temperature to ensure a tight seal without deforming the product. Depending on brand positioning, the packaging may consist of craft paper, branded printed paper, or transparent BOP film. All packages are automatically cut, labeled, and printed with batch codes, production dates, and origin information. The packaged soap bars are then placed into moisture-resistant carton trays, sealed with inspection labels, and transferred to storage for shipment. This final stage completes the entire production line, the moment each soap bar leaves the factory in its finished form, ready to reach consumers. After sorting, rigid plastic bottles are fed into a shredding chamber where hundreds of alloy steel blades spin at extreme speed, producing a sharp, piercing noise that echoes through the factory. In moments, each bottle is ripped into countless uniform fragments only a few inches long, small enough to slide along the conveyor like a stream of glittering plastic sand under bright lights. The sheer power of these machines is astonishing. Each hour, they can process up to 3,000 pounds of plastic, quickly transforming mountains of bottles into tidy flakes within minutes. Shredding does more than reduce size. Finely chopped plastic melts far faster inside the extrusion furnace, saving up to 40% of energy compared with melting whole bottles. As a result, the entire production line runs faster while significantly lowering operating costs, creating a strong foundation for the next stage of high-tech sorting. This efficiency makes large-scale plastic recycling faster, cleaner, and more economically sustainable worldwide today. From these tiny fragments, optical technology and artificial intelligence handle the most delicate sorting stage of the entire process. A network of high-speed cameras scans each piece, analyzing color and surface structure within milliseconds. When the system detects clear PET, blue PE, white PE, HDPE, or foreign materials such as wood, ceramic, or glass, a burst of compressed air is instantly triggered, blowing that fragment out of the main material stream. The accuracy is astonishing. Each air jet targets a single plastic piece weighing less than 1,000th of an ounce without disturbing neighboring fragments. On average, an optical sorting machine can process more than 10,000 pieces per second with over 95% accuracy, equivalent to the output of hundreds of workers operating continuously without rest. Every second, tens of thousands of particles are separated precisely, forming streams ready for next stage. From the initial state of chaos, the material fragments are now pure enough to enter the pelletizing stage. After sorting, plastic flakes are fed into an extrusion system, where temperatures rise beyond 520 degrees. Under this intense heat, each fragment melts and blends into a thick plastic flow, moving forward like a stream of artificial lava. Inside the machine, a massive screw rotates continuously, mixing the molten material while steadily pushing it ahead. As the plastic travels along the length of the screw, pressure gradually increases, forcing the melt forward. When the material reaches the desired viscosity, it is pushed through ultrafine metal screens that trap the final impurities. At this stage, the molten plastic is cut into countless tiny pellets and immediately cooled with water to solidify their shape. Uniform in size, smooth-surfaced, they sparkle like gems. From uniform PE pellets, the manufacturing journey moves into a defined stage. Preform production, the foundation on which the final shape of the product is created. Inside the factory, material that has passed quality inspection is fed into a heating system, where temperatures rise to around 480 degrees, softening the plastic and preparing it to flow into molds. The result is a short component shaped like a test tube, known as a preform. Each preform has a thick body, while the neck is already formed with threads for a cap. Designed to withstand high temperatures and mechanical pressure, preforms maintain stability throughout transportation and subsequent processing. The advantages of preforms are not limited to technical performance. Their compact size optimizes storage and logistics, allowing millions of units to be transported efficiently without occupying excessive space. For this reason, many facilities specialize solely in preform production, supplying beverage companies, where they are blown into finished bottles closer to points of consumption. When the preforms are ready, they enter a decisive stage, blow molding, where they take on the true form of a plastic bottle. The preforms are fed into a heating system, warmed just enough for the plastic to become flexible while maintaining structural stability. Immediately afterward, high-pressure compressed air is blown in through the neck, causing the plastic walls to expand evenly and press tightly against the metal mold surface, precisely engineered to the desired shape. A 1.5-liter bottle preform, initially only about 10 to 12 centimeters long, can stretch 4 to 5 times its original height during the blowing process. This technique is considered one of the most precise and highly automated stages in PET bottle manufacturing. Each system can produce thousands of bottles within seconds, with deviations controlled to minimal levels. Wall thickness, cap thread accuracy, concentricity, and surface gloss are continuously monitored by sensors and computer software. The result is a lightweight bottle that remains strong enough to hold carbonated beverages, resist leakage, and maintain its shape under pressure. Beyond meeting technical standards, this process offers remarkable flexibility. Bottle volume, body curves, label placement, and even embossed logos can be customized to meet brand requirements. It is here that a simple plastic preform is transformed into a complete PET bottle, ready for cooling and packaging. Immediately after leaving the blow mold, the bottle surface remains at very high temperature, making the plastic walls soft and easily deformed if not treated at once. For this reason, production lines guide bottles into an instant cooling system. Streams of cold air or circulating water stabilize the bottle structure. This rapid cooling process allows the material to harden quickly and retain its original shape. Notably, in modern factories, cooling speed is calibrated with extreme precision. A newly formed PET bottle can reach a safe temperature in under 5 seconds. In addition, many systems recover heat released from bottles to warm water or air, saving energy and reducing operating costs. Once the plastic has fully solidified, the bottle gains mechanical strength needed for stacking, labeling, and withstanding impacts during transportation. Cooling time is calculated to avoid slowing production lines while ensuring clarity and rigidity. When the bottle body is fully stabilized, the journey continues with a rigorous inspection stage to ensure quality before the product reaches consumers. The inspection line is equipped with sensors, cameras, and high-precision measuring devices. Each product is scanned to detect cracks, air bubbles, or dimensional deviations. In addition, random samples undergo mechanical tests such as tension, compression, and impact to evaluate strength. For bottles intended for food and beverages, laboratories conduct chemical analysis to ensure no harmful residues remain. Only after passing this entire strict sequence of checks is the product allowed to move to the next stage. Approved bottles are grouped into large batches, stacked on pallets, and wrapped in protective film. Automated robotic palletizing systems arrange thousands of bottles, containers, or plastic products neatly and accurately. Each batch is labeled with traceability codes, ensuring full transparency from recycled raw materials to finished goods. Products ship from warehouses, completing a circular journey.